From the role of randomness in computation, to the foundations of complexity theory, cryptography, and expander graphs, the pursuit of understanding the fundamental principles governing the theory of computation has driven researchers to push the boundaries of what is possible. Join us as we hear from Avi Wigderson, the 2023 ACM A.M. Turing Award recipient, whose groundbreaking work has reshaped our understanding of the field.
Theory of computation, which is basically the mathematical foundations of computing. You study the power and limitations and properties of various computational models. This theoretical work, often guided by completely non-practical matters, by curiosity, by following your nose, is fundamental not just for itself, but almost always turns out to find applications. Around the 1970s, people started inventing probabilistic algorithms. There were problems that there was no efficient algorithm which was deterministic, and people had the idea that maybe, like in statistics, you make some random choices in the algorithm, this may allow to solve things faster. Like in a population survey, you ask a few random people and you get a good sense of what the whole population thinks, so it's much more efficient. Around the early 80s, people in Berkeley, mainly Manuel Blum and his students, realized that under some assumptions, you can simulate randomized algorithms by deterministic ones. I learned about this, and together with Noam Nissan, we built what's called a pseudo-random generator, or something that is deterministic but looks like it's producing random numbers from just standard assumptions in the field that are related to this P and NP problem. NP versus P asks the question of whether everything that can be easily verified can also be easily found. It completely contradicts intuition, at least. I mean, if you lost your keys, in a forest, we don't know a better way to find it than go and search everywhere. But if somebody happens upon them and they come, here are your keys, you recognize your keys. So it seems that verifying that the solution is correct is much easier, and finding it is much harder. I think the connection to creativity is that sometimes people find things like mathematicians find a proof of a very difficult theorem, and it seems like it was creative. It's not clear to me. I mean, clearly his process was an efficient process. This is why it's important that every process, can be thought of as a computational process. Let me agree with Marvin Minsky. To me, everybody is a machine. We are born with our brains, which is some platform, and with an initial algorithm, maybe it's a learning algorithm, and then we experience life. I have no problem with the world being completely deterministic. There are two issues. One is, what is the real world like? And the other, our subjective experience. So I'm debating whether to go to movie A or movie B. I seem not to know which one I'll choose. It seems like I am choosing it with my own free will. Maybe it's all dictated. Maybe the processes in my mind could be, predicted completely. It wouldn't change my subjective feeling. What we feel, randomness in life, luck, chance, is all subjective. And it's our interpretation of what's happening, whether it's deterministic or not. Anyway, that's my view. I had arguments with lots of people about it, but it's fun. A really beautiful and important thing about this area of complexity theory, theoretical computer science, is that indeed different parts of it, which seem to talk about different subjects and different structures, are actually very well connected. And the import of ideas between different parts of the field led to major breakthroughs and progress. Expander graphs, for example, initially their purpose was being robust networks. But then they turned out to be essential in many different parts. They found applications in cryptography. They found applications in various algorithms, just making the algorithms more efficient. People found ways to make from them error-correcting code. I find it quite amazing that I'm more than 40 years doing research, and I'm still being surprised and sort of awed by beautiful things that people are doing. And a problem can stand 30 years without a solution, then somebody sees how to overcome the obstacle. What I tell my students, my postdocs, young people, is that research is a great life, but still not for everyone, because the normal experience of a day's work is failure. But of course, it's easy to enjoy the discovery, but I think I and many other researchers, I think, are there because they also enjoy just thinking about problems and trying to understand them, even with the understanding that it may be months till something will come up, or it may be months till you give it up and go to something else.